Hello and welcome back to our deep dive into the world of data structures and algorithms. Today we're tackling a crucial concept that ensures our data structures remain efficient and performant. Balanced trees. We already seen trees and also touched upon basic tree operations like searching, inserting, deleting and traversing. But there's a significant challenge with simple binary search trees that we need to address. Their efficiency can dramatically decline if they become unbalanced. First, why is balancing important? Imagine building a search tree by inserting elements in a specific order, like always inserting larger numbers. In that case, your tree might end up looking less like a tree and more like a linked list. This is what we call a degenerate tree. In such a tree, the time it takes to find, insert or delete an element can become proportional to the number of elements, or big O of n. Ideally, trees offer logarithmic time complexity with big O of log n for these operations, and that's where balanced trees come in. They solve this by keeping the tree's height logarithmic. So what exactly is a balanced tree? Simply put, a balanced tree is a binary search tree, where for every single node the height difference between its left and right subtree is at most 1. This property is crucial for maintaining efficiency. A more strict definition is a completely balanced tree, where all leaves reside on the same level. So this binary tree is completely balanced. To achieve this balance, these trees require specific rebalancing operations every time an element is inserted or deleted. This ensures that the tree's height remains logarithmic, guaranteeing optimal performance. There are several sophisticated approaches to achieve and maintain tree balance. Today we'll focus on the AVL trees and the 2-3-4 trees. And in the next video, we'll deal with the red-black trees and the B trees. AVL trees are basically binary trees that are always balanced, while 2-3-4 trees aren't binary, but therefore they're completely balanced. Red-black trees are binary trees that are almost completely balanced, and B trees are not binary but completely balanced. Let's start with the AVL trees, named after their inventors Edison-Velsky and Landis, who introduced them in 1962. The defining characteristic of an AVL tree is the AVL criterion. For every node, the absolute difference between the heights of its left and right subtrees must not be more than 1. The tree initially follows the standard insertion algorithm. However, if this insertion causes the balance factor of any node to become -2 or +2, the AVL property is violated and we need to perform rebalancing. To fix these violations, AVL trees use specific operations called rotations and double rotations. There are 4 main problem cases for insertion: inserting into the left subtree of a left child, the right subtree of a left child, and their symmetrical counterparts on the right side. For simple cases like left-left or right-right insertions, a single rotation either left or right is sufficient. For more complex cases like left-right or right-left insertions, we perform a double rotation, which involves 2 single rotations. These rotations are clearly designed to rebalance the tree while preserving its crucial search tree property. The algorithm essentially involves searching for the insertion point, adding a new node, and then recursively checking and balancing nodes on the path back to the root. So let's go for an example. In this case, we have to perform a right rotation because the left child of the left subtree is too tall after an insertion. So because the X subtree is too tall, the root has a height difference of +2. If it was the right subtree on the right child, it would be -2. To rebalance the tree, we rotate all nodes to the right, so A becomes the new root and B becomes its right child. Also the Y subtree becomes the left child of B to maintain the search property. Now the node 8 has a height difference of 0 and our tree is now balanced. We'd have the right-right case if A was the right child. It's exactly the same, only that we have to perform a left rotation. Next we have to perform a double rotation for the case left-right, because the right child in the left subtree is too tall with height difference of +2, which means the tree is imbalanced around node B, so C becomes the new left child of B, and A becomes its left child. Also X moves to A, so it becomes the right child of A. The situation resembles to a left-left case, therefore we perform a right rotation, so C becomes the new root, A its left child and B its right child. Again Y moves to B to maintain the BST property. And again our tree is balanced. We'd have the right-left case if A was the right child, and it's also exactly the same, only that we first have to perform a right rotation and then a left rotation. Now let's introduce 2-3-4 trees. Unlike binary trees that only have 2 children, 2-3-4 trees are multi-way trees. This means each node in a 2-3-4 tree can hold more than 1 key and also have more than 2 children. A 2 node holds 1 key and can have 2 children, a 3 node holds 2 keys and can have 3 children, and a 4 node holds 3 keys and can have 4 children. The search tree property is also present here, so all keys in the left child are smaller than the left key of the parent, the keys in the middle child are between the left and right key, and the keys in the right child are greater than the right key. The remarkable property of 2-3-4 trees is that they are always completely balanced, Insertion and deletion operations are handled by splitting full for nodes, and merging nodes is needed to maintain these properties. Now we come to searching and inserting into 234 trees. Searching is almost like in a binary search tree, except the key value you're looking for is compared with all key values in the node. Insertion in a 234 tree is always performed at a leaf node. However, the key difference lies in how nodes can expand, and critically how splitting occurs when the node becomes too full. For example, if we try to insert into a 4 node. The goal is always to maintain the tree's completely balanced property, where all leaves are on the same level. If you traverse the tree and reach a leaf that is currently a 2 node, so it contains one key, or a 3 node containing 2 keys, there is space for the new key and you can simply insert it. If you traverse the tree and encounter a 4 node, it becomes a 5 node, so it triggers a split. There are 2 ways to achieve the split, bottom up and top down. For bottom up, we start at the leaf node, we want to insert the node and split all 4 nodes up to the root. And for top down, all 4 nodes on the path to the leaf node we want to insert are split it as a precaution. If the height of a 234 tree needs to be increased, this is always done on the root upwards, maintaining the complete balance. Unlike AVL trees, individual leaves are never added to the bottom, or the balance can be lost and should be restored. So in this case we want to insert 10 in our 234 tree. 10 is greater than 8, so we go right, and then we already reached a leaf node. The node is a 2 node, so we can just insert it. If we have a 4 node, we have to perform the split operation. First we have to case the 4 node as the root, then we split it into 2 nodes, and its middle key moves further up the root to its parent node. So the middle key is our new root and the other keys are the children. If the 4 node is attached to a 2 node, again the middle element moves to the parent node, so it becomes a 3 node, and the other keys form 2 nodes. If the 4 node is attached to a 3 node, again the middle key moves to the parent node, so it's a 4 node now, and the other keys form 2 nodes. Now we can quickly look at the top down and bottom up methods. So we want to insert the value 55 into this 234 tree, where we search for our insert position. We precautionally split all 4 nodes on our path. 55 is greater than 50, so we go to the right child 70. 55 is less than 70, so we move to its leftmost child. And then we reach the leaf level, so we didn't have to split any 4 nodes. But because 60, 65 and 68 is a 4 node, we cannot simply insert 55 here, as it would become a 5 node. So this node must split before we attempt to insert 55 into it. So we perform the bottom up method. The middle element of the 4 node, which is 65, is promoted upwards to its parent node 70, and the original 4 node then splits into 2 nodes. Now that the tree has been restructured, we can proceed with the insertion of 55, which finally gives us this 234 tree. In conclusion, balanced trees like AVL and 234 trees are fundamental to efficient data management. By maintaining a controlled height, they guarantee that operations like searching, insertion and deletion remain highly efficient with logarithmic time complexity, regardless of the data's input order. They prevent the performance pitfalls of degenerate trees and are the backbone of many advanced data structures and algorithms used in various applications from databases to operation systems. Thank you for watching this deep dive into balanced trees. I hope this has been clear and helpful. If you have any questions or want to learn more, feel free to reach out. Don't forget to like and subscribe for more content, and we see us in the next one.